Hello everyone, thanks for tuning in to this presentation of the Astro Huskies Lunabotics competition robot. My name is George Johnson and I am the current project manager for the Lunabotics project under Michigan Technological University's Mining Innovation Enterprise. Through this presentation I'll be showcasing the progress our team made on our competition robot over the course of the last 2 semesters. For those of you who are unfamiliar with NASA's robot mining competition, it is essentially a competition hosted at the Kennedy Space Center in which 50 college and university teams from across the U.S. compete with their lunar excavation rovers. This competition is intended to engage undergraduate students in the process of developing a vehicle that could be sent to the moon to excavate lunar dust, rocks, and icy lunar chunks. Through these challenges, teams have to meet specific requirements such as mass and size limits, power and communication constraints, as well as developing a certain level of autonomous operation. This past year was MTU's first year participating in this competition, and despite the cancellation of the competition, we made significant progress on designing and building a robot to compete. Taking a systems engineering approach to this project, our team began the fall of 2019 semester by reviewing the competition rules, constraints, and point value system. Using these, we were able to define characteristic engineering requirements to guide our design process. These requirements centered around the mass limit of 60 kilograms, the initial starting dimensions of 1 meter by half a meter by half a meter, and a minimum 1 kilogram gravel collection, power and communication limits, and various autonomous requirements. After defining our general engineering requirements, our team took the first step in generating design ideas, utilizing a morph chart to consider various possibilities for excavation systems, chassis and drivetrains, style of wheels, autonomous vision systems, and material handling systems. From this morph chart, the Astro Huskies broke off into 3 design groups, distinguished by different excavation systems, to develop possible design considerations. One of the initial design considerations centered around a circular scooping excavation system, shown here as Design A. This design consisted of one excavation piece that would essentially start in a horizontal position near the top of the frame and rotate while also actuating down. Analysis of this design noted its simplicity and ease of manufacturability, as well as the large torque requirements and excessive power. The second of the initial design considerations, Design B, was based on an auger excavation system. This auger would screw into the ground, actuate out, dig multiple holes collecting regolith and gravel pieces. The material would flow up the auger and into a hopper area with a mesh to allow the regolith to fall out and retain the gravel pieces. Simulations of this design showed us it had a relatively low duty cycle and had the capacity to reach the full depth of 30 centimeters. However, this design also required an excessive amount of torque and power consumption. Leading us to the third design consideration, Design C, a bucket elevator excavation system. This design utilizes a more efficient method of trenching, taking smaller scoops of regolith and depositing them in a hopper on board the robot. This design was considered to be the most feasible as the power consumption was lower relative to the other 2 designs and was considered easier to manufacture. Our chosen design did indeed end up being the bucket elevator, as we used a point evaluation method to choose from the 3 considerations based on the engineering requirements we had set at the beginning of the design process. At the end of the fall 2019 semester, we had a comprehensible robot design with enough details to estimate the total mass of the robot to be around 52 kilograms, which is less than the mass limit of 60. Further work has been done on this design during the early weeks of spring 2020 semester, before we eventually transitioned into the building phase of our Lunabotics project. Over the course of the last 2 semesters, significant progress was also made on the robot's vision and mapping system. This will aid us in the autonomous portion of the competition once it is further developed. The theory is simple. By using this colored beacon placed at the location of the lander or drop-off point, the robot vision system will be able to discern 2 to 3 colors at any point on the field and thus be able to determine its position and orientation based off this one visual. We also intend to use this visual system to track and map the field and obstacles such as rocks and craters. Now that the fall 2020 semester has begun, our team, the Astro Huskies, have dove back into the building phase. Much of the robot's frame and bucket excavation pieces have been manufactured and are currently being assembled. We expect to have our robot fully assembled by the end of October and begin a series of tests in the Husky Works Planetary Surface Technology Development Lab soon thereafter. We're all very proud of the progress we've made on this project so far and hope to make it to the 2021 competition. Thank you all for listening in on this presentation about the Astro Huskies Lunabotics Mining Rover project.